Okay,
Okay, so our last talk of this session is by Bhavik Mehta, and he's going to talk about formalization of combinatorics. Take it away.
thank you very much. I just want to say at this point, if anyone has any questions, feel free to just shout out and interrupt me, and I'll be happy to answer anything. Um, okay, so I want to talk about some work I did last year on formalizing combinatorics, in particular, a breakthrough in Ramsey's theorem. So what does Ramsey's theorem say? We're going to fix some naturals K and L, consider the complete graph on n vertices. We're going to color each of the edges of this complete graph either red or blue. There are some obvious questions we can ask about this. Must there always be a subset of K vertices which contains only red edges? The answer for this is fairly obviously no. You can just say all the edges are blue. Vice versa, can you always insist that there's a subset of L vertices which contains only blue edges? And again, the answer is no. But must we always have one or the other? So that means, must there always be a subset of K vertices where there's only red edges, or a subset of L vertices which contains only blue edges? And it turns out if n, the original parameter, was large enough, then it turns out yes, we must be in one of these two situations. This was first noticed by Frank Ramsey in 1928, and he didn't originally consider this as a graph theory problem. It was actually a helper lemma he used to try and solve decision problem for first order logic. He was trying to show that first order logic was decidable, and he ended up proving this along the way. We now know that first order logic isn't decidable, but nonetheless, this spawned the entire branch of maths called Ramsey theory, which is now a very active area of combinatorics. We can then define Ramsey numbers as the smallest n which works. So just to write that down explicitly, RKL will be the smallest n, so that for any red-blue coloring of the complete graph on n vertices, there's either K vertices with only red edges between them, or a set of L vertices with only blue edges between them. And Ramsey's theorem says that this is well defined. It's worth mentioning here that there's a bunch of different variants of Ramsey's theorem. The most common and maybe original one is when K is equal to L, but most of the analysis is kind of more interesting and more useful if you allow K and L to be different. You can also allow for many colors. So I've got red and blue. There are also variants where you have many more colors. And you could also consider what happens when n is infinite. And this is all covered in Ramsey theory, but I will focus on this kind of the original example of two colors in a simple graph, and everything is finite. So to give you an explicit example, this is a proof that the Ramsey number 3, is greater, that should actually be greater than 5. The reason is, here is a coloring of the graph on 5 vertices, and you can see that there's no subset of 3 vertices, which is all red or all blue. In particular, there's no red triangle, and there's no blue triangle. But I've got 5 vertices, so the Ramsey number 3 must be more than 5. And it turns out it's 6. I won't give you a proper proof here, but that's not too hard to show. So that's a small number example. What's in some sense more interesting for combinatorics is what happens for very large values of K and L. And like I said, Ramsey's original theorem showed that this is a finite number. But it's not too bad to do a little bit better. You can bound the Ramsey number KL by the binomial coefficient K plus L, choose L. I'll give you a rough idea of how that proof works in a moment. But for now, let's notice that if K and L are both equal to 3, like in the example on the previous slide, then this gives you 6, choose 3, which is way bigger than what I said it would be. But it turns out you can improve this to have a -2 at the top and a -1 at the bottom, and then you can get essentially close enough. As a corollary of that, using Stirling's formula, if K and L are equal, so we have RKK, this is called the diagonal Ramsey numbers, and which is in some sense the more interesting version, but like I say, you still need to use the off-diagonal version to prove things. We have 4 to the K over root K. So this comes from essentially writing out this binomial coefficient and then doing some Stirling approximations. And this number 4 is important because ever since this 1935 result, the number 4 hasn't really been improved. But we can still look at lower bound. So the lower bound for the diagonal Ramsey number is root 2 to the K. And at the time, this was somewhat surprising because all of the explicit constructions like the one I've showed you earlier, gave something like k squared, k cubed. I think there was one just before 1947 which gave you k to the 4. And at the time, it wasn't clear that the diagonal Ramsey number would be more than polynomial. It turns out it's exponential, so it's far bigger than polynomial, which was proved in this paper. This paper was interesting because this was the first example of probabilistic combinatorics. The proof given here is essentially pick a coloring at random and probably it will work. And that's how you prove root 2 to the k. Because this was the beginning of probabilistic combinatorics, this inequality is sometimes called the inequality which launched 1,000 ships, in the sense of it launched 1,000 papers, it launched a new branch of maths. This lower bound has essentially not been improved since 1947. It had a tiny improvement in 75, but that was only by a factor of 2, not inside the base of the power. So this number root 2 is essentially the same as it was since 1947. In terms of going back to the upper bound, we still have this 4. So in 1987, Thomason got a better improvement. So we've gone from this root k to a k. And I've rearranged this in a slightly odd looking format for comparison with the next result, which I'm about to show, which was by Connell in 2009 and then improved by Starr in 2020, which improved it slightly again. So this is now a super polynomial improvement to the original Erdős-Czechorez bound, but we still have a 4 in the base of the exponent. Nonetheless, even though we still have a 4, this was enough of an improvement in the sense that it was super polynomial that Conlon's paper got published in the Annals. So this result on its own was pretty important. But in March of last year, the base of the exponent 4 was improved. So in March 2020, a team of 4 authors managed to improve 4 to 4 minus c, where c is a small fixed positive constant. I also want to mention on the side that there was another breakthrough in Ramsey theory by Mateus and Vestreta in June last year, but this was in the off-diagonal case. That's different to what I want to talk about today, but it's another breakthrough which I wanted to demonstrate and show that these are two different things. C was about 0.001, and the number hasn't been improved a lot since then, but it's significant because it's a number strictly less than 4. So how does the proof actually go in lean? We need to define edge labelings, we need to define Ramsey numbers. If you use the inductive proof of existence, which is what Erdős and Czechorez did, then you actually get this bound at the same time, which is what I did in formalizing it. For the lower bound, you do need probabilistic combinatorics, and this is also necessary for the formalization of this new upper bound. And there's also something interesting about small values. So I've managed to convince lean of 4 of the known values for the small Ramsey numbers. It's known for 11 explicit cases, excluding the kind of trivial ones where k or l is 2. Excluding those, there's 11 values which are known. Famously, R55 is not known. But of the 11 that are known, I've managed to convince lean of 4 of them. Okay, so before I give you an idea, before I talk more about the formalization of this, so I formalize this main result, and I'll talk a bit about formalization. But I first want to give you a rough idea of how the proof works, for which I'll need to first give you an idea of how this proof works, the binomial upper bound. In fact, I'm going to give you a slightly weaker upper bound, 2 to the k plus l, but it's got all of the same ideas. And this is a form which is essentially, this is what we're going to improve to get the best upper bound now. This proof idea is usually something covered in like a undergrad or graduate graph theory course. It's fairly straightforward, but the way I'm going to present it right now isn't the standard one. It's not so different, but it's a bit simpler and it's more relevant for the rest of what I want to talk about. So what we're going to do is we're going to start off with sets A and B. We're going to start off having them empty, and X will be all of the other vertices. I'm going to take things out of X and add things into A and B iteratively. And as I do this, we're going to have X getting smaller and A and B getting bigger. But if we want to have a red clique or a blue clique, So that's vertices which are connected only by red edges. I'm going to, assuming that that doesn't exist, we must have that the size of A is at most K and the size of B is at most K. So we're going to have that, and I'm going to maintain the invariant, like I said, that everything in A is connected by red edges and everything in A joined to X is also connected by a red edge, and similarly for B. So that's our setup. The step I'm going to take iteratively is that I'm going to pick a vertex V. I'm going to look at its neighbors. I've got some red neighbors and I've got some blue neighbors. If I have more red neighbors than blue neighbors, then I will move V into A, like I've shown on the right here, and just remove all of the other vertices, the ones that are connected to V by blue edges. We're just going to throw them away. So what's happened here is X has got about a half of its original size, roughly. There's a few error terms there, but I'm going to ignore them for now. So X is about half its original size, but A has got one bigger. Now, as I keep iterating this process, I'll pick another V, look at what neighbors it has, take it into the side which is more popular. X is going to keep shrinking by, at worst, a factor of 2. And we know it can't shrink more than K plus L times, because the size of A and the size of B are bounded. So, to start off with, we must have had X being smaller than 2 to the K plus L. Otherwise, you can keep iterating this process to get a contradiction. So this iterative process, kind of an algorithm, is one of the ways of viewing the original proof of RKL is less than 2 to the K plus L. I also want to say quickly here that if K and L are equal, then I have 2 to the 2K, which is 4 to the K. So that's another way of seeing where the 4 has come from. It's interesting to note here that there's quite a bit of redundancy in this proof. For example, I didn't say how you choose V, and in fact, the proof doesn't matter how you choose V. If you pick it randomly, if you pick some random ordering, it doesn't affect the proof in any way. So it's possible to imagine that if you were to do this proof a bit more carefully, you can do a bit better. It turns out if you do the proof a bit more carefully and fix all the error terms that I mentioned, you get this 4 to the K over root K, but you still don't get anything better than 4. But the breakthrough of last year was to do something slightly different. We're going to have A and B and X just like before, and they're connected to X in the same way, but I'm also going to have this fourth set Y. And everything from A to Y is going to be connected by a red edge, but I'm not going to say anything about B and Y. The idea of this is that as I keep taking things out of X or Y and moving them into A or B, if A turns out to be big, then I've won, I found my big red clique. If B turns out to be big, then again I've won, and I found my big blue clique. But if Y ends up being big and A ends up being not too small, then by using Ramsey's original theorem inside of Y, then I must have either a small red clique or a blue clique. And once I've got my small red clique, I can join it to A, and that will be the structure I'm looking for. So this together, A and Y here, is what's called a book. It's called that because A is kind of like the spine of the book, and all of the edges from A to Y are the pages. So this algorithm is called the book algorithm because I will either find a big red clique A, a big blue clique B, or a big book. And if I found the book, then I've also won. So what are the steps we're going to do? Earlier we had red or blue steps, depending on whether I want to move a vertex into A or into B. But now I'm going to have 2 extra steps. There'll be red steps. There's a big blue step, which is where instead of doing one blue step, I'll do a bunch of them all at once. Or I could shrink X, or I could shrink X and Y and put something into B. I'm being vague here because the details aren't so important. I would encourage you to read the paper if you want more details. But the basic idea is that the density of red edges between X and Y can't become too small. Otherwise, the first 2 steps will make X much too small. And then the algorithm would terminate early. So we have these 2 additional steps, which are controlled very carefully to make sure that that can't happen. Okay, so now we've got this algorithm. Hopefully you can trust me why it works. And I want to put it into lean. What we'll do is define this in almost a very explicit way. I'll define it as an algorithm. The step number will be given by this natural n, and we'll return an option And book config here is this 4-set setup that we started with. Why is an option? Well, the algorithm must eventually terminate, and once it terminates, we'll just go to none. So we're going to start off at 0 with the initial configuration, and at the I+1 step, if the ith step was 0, is none, then we stay at none. If the I+1 step wasn't none, then you can do something with C. And this is a fairly long definition, so I've omitted it, but this is essentially the meat of the algorithm. But here's the types of how it's set up, and mu is just a parameter. That's not so important. The first thing you need to show is that this algorithm terminates. From what I've said on the previous slide, it wasn't obvious that it was. And even from the paper, they never explicitly say it terminates. So I needed to come up with a proof for that. It turns out it's not too difficult. Once we've shown that it terminates, I can define the algorithm itself, not taking values, an option, and essentially say that if once it's terminated, we'll just give it a junk value, which will be the initial state. But this ini is a junk value. The reason it's more useful to work with this rather than the option is that I don't have to deal with sums and gets everywhere. Okay, so this is the definition of the book algorithm as I've written it in Lean. So how does the proof work now that we have this algorithm? Well, there's 2 steps. First, I need to prove a bunch of properties about the algorithm, and then I need to use the algorithm to get a better bound on Ramsey's theorem. So there's a few things you need to do with this algorithm. First, you show there aren't too many big blue steps. You need to show that shrinking x and y actually is an improvement. So I mentioned that the reason you need to do this kind of step is for the red density. And you need to show that this actually works. And then I need to show that x and y end up being big. So it's obvious why y wants to be big, because then you find the book you're looking for. And it's useful to know that x ends up being big because then you know you haven't gone too small and degenerated. Okay, then you use the algorithm. So we're going to start off by picking x and y randomly, so the red density is about half, and then run the algorithm. What essentially turns out to happen if you work through all the algebra is that you've got an improvement on the upper bound of 4 to the k in the case where this red and this blue region are disjoint. And it turns out that the larger the gap between them is, the better improvement to the bound you found. So if they're very disjoint, then I've maybe proved like 3.5 to the k. If they're touching exactly, then I've proved 4 to the k. And if they're overlapping, then I've proved 4.2 or something to the k. And if you just run the book algorithm directly, in the same way that we did with the original basic algorithm, turns out this fails. And it's possible just about to see that there is a green overlap between the red and blue regions. So after all this work, after this complicated algorithm, after this 40-page analysis, it turns out that this didn't quite work. We have this slight overlap, but fortunately, this overlap only happens in the case where L is a good fraction smaller than K. So the trick is that we run the book algorithm again in that specific case to give an improved upper bound to the Ramsey number in this off-diagonal case. So the significance of this equation I've written here is that if this leading term was omitted, then I have the original bound. But, there should be a minus sign at the front, which is kind of important. There should be a minus sign there, which means that I've got an improvement in the special case where the ratio between L and K is sufficiently small. It turns out once you do this, the graph changes a little bit because I know that in this particular case, I've got an improvement to the Ramsey number. What happens is you get a tiny shift. It's tiny, just about visible here, which makes these 2 regions distinct. I've zoomed in on it here. I apologize for the pixelation, but this jump here isn't pixelation. This genuinely appears in the analysis. So that tiny jump is what makes the 2 regions disjoint and gives us the upper bound to Ramsey's number. So this is not a particularly pleasant proof, and I think it's sensible to imagine that Lean doesn't quite like this. It turns out it's completely possible to formalize, but there's quite a bit of awkwardness along the way. In particular, for this last few steps where you have these numerical calculations and graphs, you need fairly precise approximations to get this all to work. So it turned out that I needed to approximate the natural logs of 2, 3, and 5 up to 30 decimal places, and the binary logarithm of these 2 very specific rational numbers up to 5 decimal places. And then using those, do some interval arithmetic and some calculus to get that the regions actually are disjoint. One thing which helps is that you can see on here, there's a straight line which separates the two regions, which helps a huge amount because that makes it essentially a one-dimensional problem rather than a two-dimensional problem. But after all that, it does work. So I ended up managing to prove that there exists a k essentially large enough so that the Ramsey number of kk is at most 3.999 to the k. For those of you who've done almost any analysis in Lean, you'll know that I could have written this as a filter, and the actual version does use that. I just couldn't get it to work in Beamer, so this is what you get. You can also get a version which works for all k at the cost of losing some explicitness in what the constant was. And so this bound here is the claimed result from the abstract of the paper. And this is all completely formalized. Okay, so what do we learn from this? Very recent combinatorics is very accessible to verify. This is a proof from 2023. I managed to formalize it within about 5 months, and the proof took about 5 years for the team of 4 authors to find. And it's been an open problem since the 30s. But it's still very accessible to verify in Lean, even though some of the stuff is a little bit awkward to do. I mentioned numerical calculations being tricky. There's also some specific asymptotics which are tricky. So Lean is not too bad at writing stuff and stating things about asymptotics, but doing it with very explicit functions is a little bit tricky. This is one of the things where Isabel, I think, is doing a little bit better than Lean, and so it'll be interesting to try and port some of their tactics over to Lean. And MATLib is rapidly growing and improving. So all of this stuff I'm actively trying to get into MATLib. In particular, Ramsey numbers are fairly important, and even edge labeling would be very nice to have. Okay, that's everything I wanted to say. I hope if anyone has any questions, they're very welcome to ask them. And I just wanted to thank the organizers for letting me talk at this, and also for the MATLib community for helping set up simple graphs and Lean in general to make all of this work very nicely. Thank you very much.
Okay, very nice. Are there any questions? I see a question by David. Yeah.
I was clapping my hands, not raising them.
Clapping, sorry. Clapping. Kevin has a question.
Did you find any mistakes in the paper?
There were a couple of tiny mistakes, but nothing significant. The main sort of stuff which was annoying is that most of the analysis is for sufficiently large K and L, and sometimes this wasn't explicitly mentioned in the paper, which isn't a huge problem, but it makes it a bit awkward to formalize. In terms of numerical calculations, everything worked out fine, which is kind of surprising because when I asked the authors, was there anything that you are uncertain about in the paper? It was this graph and these precise calculations that they were uncertain about. It turned out that was all completely fine. I think all of the problems were easily fixable, and it was just a problem of they were slightly less rigorous than I would have wanted them to be.
Rob?
So I think it's really cool that this stuff can happen in, let's say, near real time at this point. There's still kind of a selection process, right? And that probably not every combinatorics paper being published now can be formalized in near real time. But like, do you think we're at the point where there is more than enough like real-time stuff to occupy formalizers? And kind of related question, so two things at once. Do you think that like, is formalization helping the combinatorics at this point, or is it close to helping the combinatorics? Or are we still kind of far off there?
Okay, so for the second one, I think we're a little bit far off from that. One very particular thing in this example is that I mentioned this constant was 3.999. All of the authors are fairly certain it can be improved. Some of them say to 3.85 or 3.8. And the reason that that hasn't been done is the analysis is kind of tricky. It's kind of awkward to manage all the constants to figure out what's going on. It would be nice in principle if Lean could help doing that, because Lean would, you can write down everything. You can be sure you haven't made any mistakes. Everything's very explicit when you've written it in Lean. But it's unclear if that's something which is viable at this point, because there's kind of more awkwardness along the way than there would be on paper. So as much as I would like that to happen, I'm not sure we're quite at that stage just yet. As for the first thing, there definitely is a selection bias. I think I would say that the majority of papers can be formalized in real time, but not all. My reason for it being not all is that if there are papers which use ideas from other areas of maths, then they become quite a bit more difficult. There was a paper from, I think, 2022, maybe 2023, which used some results on the Weyl conjectures to do combinatorics. And since we're pretty far from those, doing that combinatorics paper is pretty tricky. There are some others where you need to use a SAT solver in order to prove some particular results. And as far as I know, that's not completely convenient to do in the context of MATLAB 4 at the moment. So the kind of examples where I think it would be tricky is where the prerequisites aren't yet formalized. But the argument itself, I think if you assume the prerequisites from other areas of maths, it's probably fairly doable.
Cool. That's exciting. Thanks.
Yeah.
Are there any other questions?
Maybe I can follow up on my, I don't know, the first question of mine that you answered just quickly. So in terms of making this useful to the combinatorialists,
yes,
what needs to improve about Lean in order for this to be possible? Are we missing tactics? Are we missing like organizational tools? Are we missing library stuff? Is it just that it is too hard to formalize right now? Like,
I would say a combination of almost all of those. So tactics is one thing. So I mentioned this thing about asymptotic calculations. I've seen some parts of this paper have now been formalized in Isabelle. And along those, there are some asymptotic calculations which were just done by one tactic in Isabelle, which weren't completely obvious to do in Lean. And that's the kind of thing which you wouldn't really write on paper. So that sort of thing where if Lean made that sort of proof easier, then I think making this useful for combinatorics would be a bit easier. And then I think it would also be nice if there were more refactoring tools available. So, for example, some IDs for other languages, not proof-resistant languages, it's not too hard to just like highlight a name and change it everywhere it's used from the definition onwards. That would be nice to have in Lean, but I think what's more useful and probably much more difficult is to change a particular constant or a particular form of a bound and see how that propagates through the rest of the proof and how much of that can be fixed and worked out automatically. Now, I realize that's a very big ask, but that's the sort of thing which would be nice for a computer version of a proof to be able to assist you with.
yeah, I mean, I wouldn't call that a big ask. It sounds like a very useful, interesting thing to work on. It would be wonderful to have.
Yeah, I agree.